Hi, welcome back. This is the second part of the AC lecture and is the bulk of the AC topic. I'll be splitting this part into also two videos. The first video I will cover what is the power dissipation in the resistor and the mean square current. Next, I'll talk about why we need a root mean square current. Next video, I will talk about then the root mean square current and the mean power for square waves, and the root mean square current and the mean power for sinusoidal alternating current. Let's now talk about power dissipation in the resistor and the mean square current. A pure resistor converts electrical energy into heat energy. This can happen in the form of light bulb, electrical heater, or just a pure resistor. Now, if you consider the power dissipation in a resistor by a constant current, a DC, we know that power dissipated is simply given by P equals to I square R, or P equals to V square over R. The energy provided by the battery becomes heat and dissipates as heat away from the resistor. Now let's look at it and what is the power dissipated by a resistor undergoing alternating current. First, the current comes in from left to right. The current is relatively small. The power dissipated given by I square R will be relatively small. Notice the size of the arrows. If we increase the current, the power becomes larger. Increase the current again, the power becomes larger. Note that all this power is the instantaneous power. This is the power at a specific point in time related to a specific value of the current. Next, current magnitude is reduced, the power is reduced. Once again, reduce again. Next, there'll be a point where current is 0. At the next point in time, you notice that the current has changed direction. It now moves from right to left. The size of the arrows for the power dissipated, notice that they are the same as the first example of the current going from left to right. This means that the direction of current is not important for the calculation of power dissipation. To illustrate, a current of 1 ampere and a current of -1 ampere moving in the opposite direction will both produce the same amount of power for a resistor. So as you can see, the next moment in time, the current will increase, power dissipated will be increased some more, power increases, current increases to the maximum, power increases to the maximum. Afterwards, it will reduce, then becomes 0. Right, so the power dissipated in the resistor by an alternating current will change with time. As the magnitude of the current increases, the power increases. And the instantaneous power is given by this equation, as I mentioned earlier. However, imagine you are now trying to use this as a heater, as a kettle to boil water. At what power then does your kettle boil the water? If you're a salesperson trying to sell this to someone, do you tell them the instantaneous power at all times? That would be relatively difficult. Hence, we will need to find what we call the average power. We know that we can calculate the value of instantaneous power at all times. However, to let someone know the value or to have some sense of how much power will be provided, we need to find the average power. And we use this average power to communicate what the power of the object is, how much energy it uses, how much energy it gives. Alright, so average power is given by the average of P, which is given by the average of I squared R, since P is equal to I squared R. Note, however, that since R is a constant, we can then write P equals to the average of I squared times R. Since P is also given by V squared over R, we can repeat the same and achieve P is equals to the mean of V squared over R. This value, the mean of the I square, is called the mean square current. Similarly, the mean of the V square is called the mean square voltage. Now, the mean square current is the mean of the square of the current over an interval of time. Note that this is different from what a mean current is. A mean current is really not useful for calculating power simply because the mean current is equal to 0 for sinusoidal current. Take a look at this graph and I'll illustrate to you. If you look at this sinusoidal current, we know that the mean of this current will be 0 because every part here on top above the line will be equal to the part below. The average of the current will be 0. However, does this mean that the power dissipated by a sinusoidal current is 0? Since mean current is 0, that is obviously not true. Right? Hence, we use the idea of a mean square current, right? Because P is equals to mean square current multiplied by R. And we see here that the mean square current is a non-zero value. What this means is that the square of the mean current is not the same as the mean square current. Right? This might sound like a earful, so I say it again. The square of the mean current is not equals to the mean square current. What you're looking at here, where my pointer is pointing at, is the mean square current. If I were to square root both sides, I'm trying to say that the mean current is not equals to the square root of the mean square current. So let's look at example number 1. If we are given this graph, we are asked to find the expression of the alternating current with respect to time. Then we are asked to find the instantaneous current and power at 3 various times. From the graph, or from the curve, we see that the period is 0.02 seconds. This means that omega is 100 over pi. Since omega equals 2 pi over t, if we sub this into the waveform equation, I will then be equals to I naught, which is 1.2 in the previous graph given. The maximum value is 1.2. So I equals to 1.2 sine omega t, omega being 100 pi. To find the instantaneous current and power, all we have to do is to sub in the t into the equation, and we find the value of I. To find the instantaneous power, we sub in the value of I multiplied by the value of R, and we get the value of the power that we're looking for. So let's repeat this for part C and D. And we see that in part C, when the current is 0, the power becomes 0. And in part D, we say that although the current is now negative, to denote that it's traveling in the opposite direction compared to part B, the power dissipated is still a positive value. This is because power dissipation does not care about the direction of current. So in the previous part, I've shown you why we need to use the mean square current. That is because the mean current is not useful, and in fact, most of the time it deceives people and makes them think that there's no power dissipated. However, the mean square current has units of ampere square. When we want to compare a AC to a DC, it would be very difficult if you compare an A square value, right, a value with ampere square as the units, to another value with ampere as the units. Hence, there is a need to compare apple to apple. Hence, there's a need to introduce a term, the root mean square current. So in the previous part, we have seen that the mean square current is in fact the area under the I square T graph. Right? It's in fact the mean is the area under I square T graph divided by T in one period. Right? One of the tutorial questions, right, will concern this. This will be covered at a later part of the notes, which we will see in the square current graph. So keep a lookout for that. So like I said before, in the previous slide, we need to compare apple to apple, so that is why we need to square root the mean square current. Okay? So the mean square current is the mean of the square of the current. The root mean square current is hence then the square root of the mean of the square of the current. So let's see. The root mean square current is the root of the mean of the square current. But if you were to do this with mathematics, if you're given a curve of the current time graph, what you really need to do is to square it, take the current, square it, mean it, which is take the average, and then root it. So although we say it as a root mean square current, what we really need to do is to do it this way, by taking the current, squaring it, taking the mean, and then rooting it. Alright? Note that the voltage and the current are passing in phase. This means that the V and I varies in the same way such that they will both reach the maximum value at the same time and both reach 0 at the same time. Obviously, then they will also reach the root mean square values at the same time. Hence, the graph can be sketched in this following manner. And of course, we can say that the root mean square value of the voltage is equal to the root mean square value of the current multiplied by R. Similarly, because they are both maximum at the same time, we can say that the V0, maximum value of voltage, is equal to the I0, the maximum value of the current, multiplied by R. So in the previous section, we have learned that the average power, or the mean power, is provided by the mean square current, multiplied by R. This just means that the mean power is equal to the root mean square current squared times R. Simply because the mean square current with a square root is a root mean square current. This is the first time you see the word RMS. Okay, so this is the subscript that we use very often to denote the root mean square current, RMS. Since P equals to RMS squared R, we can also say that P, the average power, equals to V RMS multiplied by RMS and V RMS squared divided by R, because V and I are in phase. Now we need to define what is actually a root mean square current. If you look at the equation, P is equal to IRMS square R, we see that if the alternating current is to be replaced by the constant current of the value IRMS, the power generated will be the same. That is to say, an alternating current of root mean square value 10 amperes can be replaced by a current of 10 amperes DC to produce the same output. This is in fact how we define the root mean square current. This is a mouthful, so try to follow me. The root mean square value of an alternating current is defined to be the value of the DC, the value of a steady DC, that if used to replace the AC, will generate heat in the resistor at the same rate as the AC. Okay, I say again. The root mean square value of an AC is defined to be the value of the steady current that, if used to replace the AC, will generate heat in the resistor at the same rate as the alternating current. That means the DC, if you use it, you'll produce the same heat as the AC was producing before at the same rate. Right. At this point of time, cover up the definition, try to repeat out a few times, press pause, do not go on unless you can master this definition. Right? So press pause and try it out a few times. Okay, we have reached the end of this part of the middle, right, the second portion of the AC. In the next video, I'll tell you more about the root mean square current for square waves and the root mean square current for AC. This will be two cases that we'll study and apply our knowledge on root mean square current and average power in more concrete terms. See you in the next video.